We are diving straight into Spatial Tree, how spatial abilities branch out in MLLMs, a really critical paper from researchers at ByteDance, Zhejiang University, and others that's fundamentally changing how we look at spatial intelligence in MLLMs.
Right, and it addresses a massive problem. Current benchmarks for spatial intelligence, or SI, are highly fragmented. They're just all over the place, and they don't really tell us how these abilities actually emerge.
So the solution here is Spatial Tree.
Exactly. It's a 4-level hierarchical taxonomy, and it's inspired by cognitive science. It's all about moving models from, a basic L1 perception all the way up to L4 agentic competence.
And the findings are, frankly, revolutionary for anyone building these models. They found this clear structural dependency. L1 skills, the low-level stuff like geometry, are largely orthogonal.
They developed independently. But the higher-level skills, L3 and L4, that's simulation and execution, they are super strongly correlated. They're interdependent.
And the training results were even crazier. They used supervised fine-tuning and saw negative transfer within L1. So focusing too much on one skill can actually hurt another.
But the transfer across levels was incredibly positive. Simple L1 skills like distance estimation provided this multi-ability synergy and gave them remarkable zero-shot gains on complex L4 tasks. I'm talking robot manipulation.
And finally, they tackle that classic reasoning trade-off. Naive reinforcement learning, just telling the model to think with chain of thought everywhere. It actually hurt the intuitive L1 tasks. Overthinking degraded precision.
So they introduced the auto-think strategy. It's a hierarchy-aware reward system that knows when to suppress deliberation for quick perception and when to amplify for complex planning. This whole thing is basically a strategic roadmap for engineering spatial AI.
Okay, let's really unpack the core idea here. The spatial tree hierarchy itself. Why was this even necessary? Why move beyond all the standard vision benchmarks we already have?
It really is about understanding emergence. If you're just testing, say, object detection, you're just looking at one siloed task. If you want to build MLLMs that are actually capable, you need a unified, a capability-centric framework to see how spatial intelligence develops.
So they're mirroring developmental psychology.
That's the idea. Think of Piaget's theory, that intelligence builds up in these successive necessary stages. They're trying to map that onto machine intelligence.
So by creating this structure, they're giving you a dependency map for how SI grows in a model. Let's start at the bottom. L1, perception. This is a raw input layer, right?
Absolutely. L1 is the most primitive level. It's that intuitive sensing of visual and geometric stuff before the model even starts using language or symbolic reasoning. It's the raw data feed for everything that comes after.
And that L1 perception is broken down into 5 distinct capacities. Let's start with geometry.
So geometry is the metric essentials. You have distance, which can be relative or precise. You have size or magnitude, and shape, understanding contours. These are just pure visual properties.
Okay, and next is motion.
Right, which is critical.
Yeah.
You had to be able to tell the difference between egocentric motion, that's your own camera moving, and allocentric motion, which is how other objects are moving around in the world.
Once you've got size, distance, and motion, the next big challenge has to be orientation. That seems especially hard for models that are mostly looking at 2D images.
It is, which is why L1 orientation is so key. It's about knowing which way is up, which way is tilted. They even use specialized tools like GeoCalib to measure gravity sensing, specifically pitch and roll angles.
And that's separate from object orientation.
Exactly. Object orientation is just pose perception, understanding the specific 3D stance of an item in space.
And then how about relating these objects to each other at this really basic level?
That's the relation subability. This handles fundamental topology. Is the object inside a box, outside it, or overlapping something else? And also, correspondence recognizing that the red ball you see now is the same red ball from a second ago, just from a different angle.
And the final piece of L1.
Localization. That's the basic grounding. Detection, and then associating what you see with actual coordinates.
That's an incredibly comprehensive set of foundational skills. So moving up from there, we get to L2, mental mapping. This is where perception starts becoming useful, where it aligns with language and memory.
L2 is the alignment layer. It has 2 main goals, understanding and memory. Understanding takes that raw perception from L1 and turns it into semantic meaning. We're talking spatial captioning, perspective taking, and critically, affordance.
Affordance being not just seeing a handle, but knowing it's graspable.
Precisely. Identifying the functional possibilities of an object. And then there's memory. L2 memory is what lets the model build awareness beyond just the immediate scene.
So you're building a global picture.
Exactly. You're constructing a cognitive map synthesizing all these fragmented views into one unified representation.
Hmm.
And you need memory retrieval, so you can recall where an object is even after it's hidden from view. That jump from L1's instant sensing to L2's retained language-linked knowledge is it's vital.
Now we get to the planning stage. L3, mental simulation. This is where the model starts doing its chain of thought before it acts.
L3 is the dry run. It's what lets an MLLM predict what's going to happen next. They break this down into causal reasoning, which is about modeling spatial interactions, physical dynamics, how shapes fit together, motion prediction.
And then taking those predictions and actually making a plan.
That's L3 sequential planning. It's the ability to design these high-level, step-by-step strategies and express them in language. Pathfinding, route generation. It's all about making sure the conceptual steps will achieve the physical goal.
Which brings us all the way to the top. L4, Agentic Competence. This is where the rubber meets the road.
L4 is the final test. Can the AI translate those complex L3 plans into real actions in a dynamic, embodied environment? The paper was super meticulous here. They curated data across 3 different embodiments: character navigation in games, robotic grippers, and human hands.
I noticed they did a lot of work to standardize the output actions with this action mapping strategy.
Yeah, you have to. For evaluation, you can't just have raw joint movements. They discretize the low-level actions into high-level motion primitives. Think of camera controls, truck, dolly, pedestal for translation, and pan, tilt, roll for rotation, plus the gripper control. It makes the MLLM's output directly comparable and, executable.
That taxonomy is remarkably comprehensive, but, just structuring the concepts is only half the battle. They then had to build a benchmark, SpatialTree-Bench, that was powerful enough to actually measure all of these capabilities.
And that's where the engineering effort really is impressive. They didn't start from scratch. They unified and reorganized a bunch of existing benchmarks like VSI-Bench and MSI-Bench, and then they strategically added to them with a new data set they called Spatial Plus.
And Spatial Plus was clearly meant to fill the biggest gaps, right? Especially that L1 orientation and L4 agentic competence. But how on earth do you annotate data at this scale with these complex spatial properties without a massive amount of human labor?
They build something they call the Spatial Engine. It's basically an integration pipeline that uses specialized expert models. For instance, using depth anything to get accurate depth maps, or GeoCalib, to automatically generate ground truth gravity vectors.
Ah, okay. So this engine let them generate huge amounts of high-quality annotations automatically, which they then just fed into LLMs with some QA templates to build out the benchmark questions.
Exactly. And the evaluation metrics themselves had to be just as diverse, given the range from multiple choice topology questions to precise numerical planning for a robot arm.
A single accuracy score just wouldn't cut it.
Not at all. About 70% of the benchmark is standard multiple choice, which is fine for the low and mid-level skills. But for the precision tasks, they needed highly customized metrics.
For something like distance estimation, mean relative error is pretty standard, isn't it?
Yes, for numeric accuracy. But the orientation metrics were a masterclass in handling real-world ambiguity. See, when you measure pitch and roll from a scene, the ground truth itself has some inherent uncertainty, what they call sigma call. You can't penalize the model harshly for being a tiny bit off when your own measurement is a little fuzzy.
That makes perfect sense. So how did they account for that fuzzy ground truth?
They used a probabilistic approach. They calculated a normalized similarity score using a Gaussian kernel. It effectively gives the model a bit more wiggle room when the ground truth measurement itself is less certain. It's a very smart way to make sure you're judging true spatial awareness, not just measurement noise.
And for L4, agentic execution, you're not scoring a single number, you're scoring a whole sequence of actions.
Right, so that required a compound score. The stepwise accuracy, or step dollar. This metric combines 2 things. The relative distance accuracy, so how close the action got to the target, and the cosine similarity of the movement vectors. Did the model move in the right direction? It gives you a really holistic, quantitative view of the planning quality.
And when they ran the big models on this benchmark, the value of this structure became immediately obvious. Thinking models, like Gemini 2.5 Pro, generally did much better than the non-thinking ones.
Right. Gemini 2.5 Pro led the pack, but the open source Qwen 3 VL235B also showed really strong performance. This initial sweep just set the stage for the really interesting discovery, the structural dynamics of the tree itself.
Which takes us right to the core of the paper. Uncovering the rules of the road for how spatial skills develop using correlation and transfer analysis.
Let's start with that correlation heat map. The finding that L1 abilities geometry, motion, relation are mostly orthogonal is genuinely surprising. You'd think improving one foundational skill would naturally boost all the others.
But that's not what happened.
No, that assumption was wrong. Orthogonality means they have weak correlations. It suggests that these fundamental perceptual mechanisms are sort of independent components in the MLLM's architecture. Getting better at sensing distance might not spontaneously make you better at tracking motion. They have to be trained separately.
And the complete opposite was true for the higher levels.
Yes, L3 simulation and L4 agentic skills showed strong correlations. That points to a deep interdependency. If a model is good at planning a route, it's very likely to be good at executing that plan with a robot arm. These complex skills clearly share some profound underlying prerequisites.
This structure immediately tells you how you should probably train these MLLMs. They tested this with targeted supervised fine-tuning on specific L1 skills. And this is where we get that really counterintuitive result, negative intra-level transfer.
It's a classic specialization trade-off. When they trained a model to be laser-focused on just one L1 skill, it often had negligible gains or even harmed its performance on other L1 abilities.
So training on distance, for example,
Resulted in a 5.8-point drop in relation skills and a 4.6-point drop in localization.
So it's like specializing a race car for drag racing. It gets way faster in a straight line, but now it's terrible at taking corners. The model is sacrificing one low-level capacity for another.
That's a perfect analogy. But the trade-off was worth it because of the second and much more dramatic finding. Strong, positive cross-level transfer.
This is the part that really grabbed my attention. Training on that simple, localized L1 distance skill led to significant zero-shot gains at the higher levels. It boosted L2 understanding by 2 points, and crucially, L4 goal execution by 3.4 points.
Wait, so a basic L1 skill trained on static synthetic Q&A scenes somehow made the model better at complex dynamic robot arm manipulation? That's a huge leap.
Well, the paper gives a clear mechanism for it. Better metric awareness in L1 just directly translates into making better control decisions in L4. If the model has a more precise sense of how far away the object is, it can generate a more reasonable and accurate movement primitive.
They quantified this really beautifully with a qualitative example. Training on simple distance Q&As gave them a 36% zero-shot gain on complex distance reasoning in totally new in the wild scenes. And even more striking, that refined distance sense led to a 27.1% performance gain for the robot arm tasks.
It just proves that foundational L1 perception is the crucial zero-shot prerequisite for agentic competence.
And we can't miss the second key finding from that SFT analysis, this principle of multi-ability synergy.
Right. Training on single abilities only had a limited overall impact.
But when they combined the SFT on all three of those fundamental abilities, distance, size, and correspondence, the gains weren't just additive, they were synergistic. The whole was greater than the sum of its parts, which really reinforces the idea that spatial intelligence needs a whole composite set of fundamental skills, not just one optimized superpower.
That idea of synergy leads us directly to the final piece of the puzzle, optimizing performance with advanced training, like reinforcement learning. As you mentioned at the COP, the core challenge was this dichotomy between thinking and perceiving.
It's the critical trade-off every MLLM builder faces. Chain-of-thought style reasoning, which is, naturally encouraged by standard RL, is fantastic for L3 planning. It forces the model to calculate. But for L1 intuitive perception, like quickly estimating the distance between 2 points, that same deliberation is actually harmful. Overthinking kills precision.
The system has to know when to trust its gut versus when to slow down and do the math.
Exactly. So they needed a mechanism to differentiate the cognitive approach based on where the tasks sat in the spatial tree. They used reinforcement learning with verifiable rewards, specifically the GRPO method, and fine-tuned their base model on the L4 robotic arm data.
And the breakthrough was this hierarchy-aware reward mechanism, which is what powers the auto-think strategy. They basically hard-coded the rules for when the model should reason.
So how did they tell the model to stop thinking?
For the intuitive L1 perception tasks, they actively removed the rewards for the thinking process and even introduced a length penalty. This forced the model toward immediate, fast, visual text alignment. It's like teaching the model to rely on reflex.
Whereas for the complex L3 and L4 tasks, where deliberation is absolutely necessary for planning, they kept and even amplified the rewards for generating those explicit reasoning steps.
And the results just completely validated this strategy. The model trained with the hierarchy-aware strategy, the full RL at AutoThink, got the best overall gains, an impressive 3.6 points overall. It significantly outperformed the naive full RL at think method, which just applied chain of thought everywhere.
This proves that spatial intelligence is not a flat structure. L1 needs speed and intuition, while L3 and L4 demand careful, deliberate calculation. And for the technical folks listening, it's worth pointing out how robust this was. They used strict data decontamination, and the training objective, the MCQ reward, was totally different from the testing metrics like MSE or execution success rates.
The fact that the gains generalized so powerfully suggests the model really did internalize these robust, hierarchy-aware spatial reasoning policies.
So to summarize, SpatialTree really provides MLLM researchers and engineers with the first truly capability-centric, rigorous framework for spatial intelligence. It shifts the entire discussion from just task performance to a real structural understanding.
Right, it reveals the prerequisite nature of that foundational L1 perception for achieving robust L4 agentic competence.
And the practical roadmap for builders is incredibly clear. Scaling spatial intelligence requires a dual approach. You need that targeted SFT on synergistic L1 skills to build the foundation, and then you need a hierarchy-aware RL strategy that respects the trade-off between intuitive perception and deliberate planning.
This whole body of work highlights a fascinating and, frankly, a cost-effective implication for how we develop MLLMs in the future. The discovery that foundational L1 skills, like geometry distance, can give you these huge zero-shot performance gains. I mean, remember that 27.1% jump in robot manipulation.
It suggests that our current complex agentic failures might not actually stem from bad planning algorithms.
So here's a final provocative thought for you to explore. If debugging and improving our spatial AI agents means we have to look past the high-level planning layers and instead focus back on the most primitive basic perceptual systems like metric depth sensing or object orientation, what other fundamental, seemingly simple L1 skills are silently gating the performance of our most advanced agentic MLLMs? The tree may need deeper roots before its computational branches can truly bear reliable fruit.